Hello, and welcome to Agrosive Physics. Today is day 120. And what I'd like to do today is calculate a few sample problems using energy. In fact, what we'll look at is a pool pump and a nightlight and see what happens when we leave them on for a certain number of hours per day. Ultimately, what we can do is calculate the number of kilowatt hours that they'll use, and then we can determine how much money it will cost to leave them on. This is very similar to what the power ratings for Energy Star labels will give you when you're buying new appliances. In fact, those values can be used to do some sample problems. And I think what we're going to do in my classes is actually use the Energy Star labels to calculate some values. Now, if you have a new appliance that you have at home, don't throw out those yellow tags. You can keep them. And now that you have the skills to calculate power and energy with electricity, you can use the variables that are given on those sheets in order to calculate to see whether or not they're accurate. So at this point, what we're going to do is take out the whiteboard and do a few sample problems. We know the power equation, which is P equals VI, or I squared R, or V squared over R. And we know the energy equation, which is E equals PT, which is VIT, which is I squared RT, or V squared over RT. And if we use those in conjunction with the V equals IR equation, we're pretty much set for most of the problems that we'll be faced with when dealing with Ohm's law and energy. Let's look at the whiteboard now. Thank you. What we're going to look at is a couple of sample problems. And these are from your notes. So we have a TV and it's going to draw 2 amps. So I is 2 when connected to a 120 volt source. 120 volts is V. What's the power output? Well, power, we have 3 versions of our equation, but I'm going to use VI. 120 volts times 2 amps is 240 watts. How much energy is used that the TV is turned on for 7 hours per day for 30 days? All right, so it's 7 hours times 30, which is going to be 210 hours, times 3,600 seconds. 210 times 3,600. All right, 756,000 seconds. So energy is power times time. Power is 240. And 756,000 seconds times 240. So the total power, the total energy is 1.8144 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 joules. How much money does it cost if it costs 11 cents per kilowatt hour? So kilowatt hour is 3.6 to the 6 joules per kilowatt hour. So I take that number and divide by 3.6 E6, and I get 50.4 kilowatt hours. Now, if it's 11 cents per kilowatt hour, you multiply that by 11 cents, and we get $5.544. So $5.54. We'll round that hundredth down. So $5 to keep that TV on for 7 hours a day for a month. All right, now we have a 5-watt light bulb. So the power is 5 watts, and that's going to be connected to an outlet, 120 volts. It's going to be left on for the month of February. So we have 28 days, and that's going to be times 24 hours times 3,600 seconds. So 28 times 24 times 3,600 gets us a total time of 2419200 seconds. That's our time. And how many kilowatt hours of energy are used. So the power is the only thing that matters. This V is extra information, but E equals PT, 5 watts times 2419200 seconds, 5 times second answer. So the energy is 1.2 times 10 to the 7 joules in this case. I'm going to divide that by 3.6 times 10 to the 6 joules per kilowatt hour. And I get the energy is 3.36 kilowatt hours. Now, if we multiply that by the 11 cents, it costs $0.37, so 37 cents to keep that light on for the entire month. So I guess I shouldn't be yelling at my kids when they don't turn off their night lights all the time. All right, this next one is about a pool pump. And what we have is a 1.5 horsepower pool pump. Now you have to remember the conversion, 1 horsepower, is 746 watts. So 1.5 times 746 is 1119 watts. So that's our power. And what we're doing is we're keeping it on 8 hours per day for a week. So 8 hours times 7 days. So 8 times 7, I don't know why I'm using the calculator, is 56. 56 hours times 3,600 seconds. And you get 21,600 seconds total. So power times time gets me the energy. 1119 watts times 1600 seconds. And I get energy is 2.256 times 10 to the 10 to the 8 joules of energy. Divide that by 3.6 times 10 to the 6 joules per kilowatt hour. And you get 62.664 kilowatt hours. So the pool pump's going to require a lot more energy than the nightlight.